Hello everyone, I am Pushpita Chanda. I am a TA for this session and PMR PhD scholar at IIT Delhi. And so this is me, TA. I am TA for this session at NPTEL. So let us start today's session. So sorry. Today we'll discuss some gain medium for the laser. First, the gaseous gain medium, our low density gain medium, and then some solid state gain medium, and so on. Okay. So first we will discuss atomic gas lasers. Okay. Uh, Atomic gas lasers, which uses gas gain medium, is gas. It is obvious. Like the gaseous or low density gain medium are used in approximately half of the exciting commercial lasers. They are certainly very short wavelength lasers, and a gaseous or plasma medium will be used in this kind of lasers. So basically they have wavelengths from 200 nanometer to 5 micrometer commercially. They are discrete laser wavelengths over this range. Discrete laser wavelengths over this range. This is range. Okay. The most common examples are helium cadmium lasers. I will discuss their working like in a descriptive manner, but here I am mentioning some examples. Okay. Helium cadmium laser, copper vapor laser. In this copper vapor laser, the copper is heated around at 1500 degrees centigrade, and that makes the copper vapor. And that's why it comes in the atomic gas lasers. And their gain bandwidth is broadening is dominated by Doppler broadening. So basically what generally happen in atomic gas lasers are like two electrodes. There are two electrodes. They gas voltage is applied like between these two electrodes, and they are situated gain the edge of the gain medium within a long cylindrical tube. Electrodes are in the long cylindrical tube that contain atomic species in the form of low pressure gas of the order of low 1/1000 or 1/100 of atmospheric pressure. The reason the gas is low pressure, that the electron temperature is inversely proportional to the gas pressure and directly proportional to light voltage. Hence, the high electron temperatures are necessary to excite the high lying energy levels of the gas laser. So we need high electron temperature. That is why the gas pressure is so low. Then when the voltage is applied to the electrodes, the discharge between to conduct these electrodes begins to conduct through the gas, which causes an electrical current to flow within this discharge tube. Thus we this is also the mechanism for the neon signs and the fluorescent light fixture, etc. That is how the gas is produced. And as the electrons travel through this tube, they collide with some atoms which are not already ionized, and excite these atoms to higher energy levels. And these atoms radiated back to the lower levels, and if they have appropriate lifetime ratio between the upper and the lower levels, they have population inversion, and then they have gain. And this radiation between the upper level and lower level uh, give us lasing radiation. So let me repeat all the procedure again. That the two electrons are like electrodes at the opposite end of the laser gain medium. That say it is a gain medium. They are installed. The two electrons are installed within a long cylindrical tube, and the tube also contains the atomic species in the form of low pressure gas, and these electrodes are installed at the edge of the gain medium. Then when the applied voltage is applied at these electrodes, then the discharge begins to conduct through the gas, and this discharge causes an electrical current to flow within the discharge tube. And the electrons, when traveling through the tube, they collide with the atoms, and these atoms, because of the collision, the atoms goes to higher energy levels, and when they radiate back to the lower energy level, and if and there we introduce a population inversion because of this mechanism that causes the lasing effect. So let me write that here at atomic, otherwise that will not be included in the notes. So gain medium. Okay. Sorry. Um, okay. Okay. So we will discuss some atomic gas lasers. Is helium neon laser, helium cadmium laser, argon plus laser. So now we'll move to helium neon laser. So they operate in a low pressure mixture of helium and neon gas, and the laser transition occurs within the natural atomic species. The most common wavelength of this laser is 632.8 nanometer transition in the red portion of the red color light of the visible region of the spectrum. The additional wavelengths have become available are like at the green portion is 543.5 nanometer, at the yellow portion 594 nanometer, and 612 nanometer, which is in the origin orange region. And also there as a is another wavelength which is at infrared region, which is 1.5 to 3 micrometer, or you can say 15 to 3 nanometer. Uh, but this helium neon laser, they can laser around like other they can produce other kind of infrared transition, but there is not that significant commercial application. Okay. These lasers are basically continuous wave laser and have a very stable low noise output. The gain bandwidth follows the Doppler broadened emission line with FW Doppler broadening emission. Line with FW of 1.5 gigahertz. The laser cavity length of 0.3 millimeter would thus allow several longitudinal modes to be assembled simultaneously within the laser cavity. The complete laser assembly is typically about 0.15 to 0.5 meter of length, with lateral dimension of order of several tens of millimeters. It is not uncommon for such laser to operate for lifetimes up to 50,000 hours. So, like mention some specification of this laser. laser wavelength generator, which is in the west region of the spectrum. Additional wavelengths at 543.5 nanometer, 594 nanometer, 612 nanometer, 1523 nanometer. Yeah. Power of helium neon laser is 0.5 to 5 milliwatt at 632.8 nanometer lasing action. I have already mentioned the Doppler broadening. It has Doppler broadening about 1.5 gigahertz with FWHM. The laser cavity length, sorry, the laser cavity length will be about 0.3 meter. Complete laser assembly is typically 0.15 to 0.5 meter in length. Okay, and lifetime is about 50,000 hours. I am giving the specification of helium neon laser basically for your understanding that which laser can last up to like how many hours. And also the helium neon mixture is like 1:5. Yeah, okay, 5:1. Helium is greater. 5:1. The gas pressure is at kept at like 2.5 torr. Pumping method, I have already explained the method that electrodes are kept, applied, voltage is applied to the electrodes, and that's why electron discharge happen. And this electrical discharge uh, like excite the atoms to the higher molecular level. So the pumping method is electrical discharge. Electron temperature is around 15,000 to 20,000 Kelvin. Now, the mode. Later, I can describe what is TM00 mode. Upper laser level lifetime is 3 into 10 to the power minus 8 seconds. So it's a 4-level laser. So this is helium. It's 0 level. It's 20.61 electron volt. Electrical impact. State. This radiation is ionization. This is 632.8 millimeters. Yeah, so basically, when a discharge is passed to the gas mixture, electrons are accelerated down the tube. These accelerated electrons collide with and pump the helium and neon atoms to metastable states, 20.61 electron volt and 20.66 electron volt respectively. Some of the excited helium atoms transform their energy to the ground state neon atoms by collision, with this 0.05 electron volt additional energy being provided by the kinetic energy of atoms. So, the helium atoms actually help in achieving population inversion in the neon atoms. The lasing action is caused because of transition between the neon upper level and lower level, but helium is there to help in achieving the population inversion in the neon atoms. When an excited neon atom passes spontaneously from the metastable state at 20.6 electron volt to 18.70 electron volt, then it emits a wavelength of wave of about wave, or we can say photon of about 632.8 nanometer. This photon travels through the gas mixture and it is moving parallel to the axis of the tube, is reflected back and forth by mirror ends until it stimulates an excited neon atoms and causes it to emit a fresh 632.8 nanometer photon in phase with the simulating atom. Okay, this transition causes lasing action. The red light beam or the laser wavelength portion of it accepts to the partially silver end, and we get the light of the from their 18.70 level of the neon atoms, the atoms passes down spontaneously to the lower metastable state, emitting incoherent light, and finally to the ground state through collision with the tube walls. There are other energy levels between these 20.6 electron volt and 18.70 electron volt levels. The transition between them results in the emission of radiation, having the other wavelength I have already mentioned, that 1523 nanometer, 594 nanometer, and all those things. So the advantages of the gas lasers, we can discuss the advantages. What are the advantages of the gas laser over solid state laser? solid-state lasers. One, the gas lasers are in general emit light which is more directional and more monochromatic as compared to that form of solid state laser. This is what is the reason? This is due to the absence of certain effects like crystalline imperfection, thermal distortion, and scattering, which appears in the solid state lasers. I will also describe solid state lasers in some bit. Also, the gas lasers can be operated continuously because the electron impacts that excite the helium and neon atoms occur all the time, and they are capable of supplying a continuous laser beam without any cooling arrangement. Further, since the laser transition does not terminate at the ground state, the power needed for the excitation is less than in the three-level UV laser. So, three-level ruby laser is the first laser which was invented. Mm, Image light emitted is hello. Okay, my video is visible. Direction one and second. Second. Another thing, like I want to mention that the small signal gain coefficient for this laser signal coefficient for this laser is 0.15 per meter, and gain medium length is already I have mentioned that it is about zero point 0.1 to 1.1 to 1 meter length. Here the gas special and also have single as gain. This parameter, what are these parameters? They are being explained in the classes. This is between 1.015 to 1.16, and this is a tunable laser. Some lasers are not tunable and some lasers are tunables. So this is a tunable laser. So this can be done by choosing in mirrors with high reflectivity over only the required wavelength length. The we need to new laser. Now I want to discuss some mathematics, the excitation rate. Okay. So here excitation rate. In the case of an intermediate state, the excitation rate rate is represented as QU, which is N neon, as I already have shown here that the lasing effect take place between the levels of the neon. Helium is there to support neon to go to that 20.6 electron volt level. So the density of the neon atoms only contribute to the excitation rate. The frequency difference between this so and the sigma is the cross section, excitation cross section. This is neon ground state density. This is relative velocity. Velocity of helium and neon, and this is the excitation cross section. Okay, the stimulated emission cross section is about 3 into 10 to the power minus 7 meters square. So the stimulated cross section is in the range of 10 to the power minus 7 meters square, but excitation cross section is of the order of 10 to the power minus 20 meters square. Okay. So typical numbers are in is 1.4 into 10 to the power 22 meter cube. The relative velocity is 10 to the power 3 meter per second, and the cross section is an excitation cross section 10 to the power minus 20 meter square. Uh, this is excitation cross section. Emission cross section stimulated spontaneous. There is also spontaneous simulation there. Cross section is about 3 into 10 to the power minus 7 meter square. Okay, so we can like see the what will be the excitation rate. This is simply the multiplication. And like if it is enough, or sometimes you get confused if we are missing like component or not. Just remember the unit dimension analysis, that the excitation rate is in second inverse, and here we are multiplying 1 by meter cube, which is in the density, into relative velocity meter by second into cross section meter square. So it comes 1 by second, 1 by second or second inverse. So this is enough for excitation. There can be some unit list component, and that can be tricky, but otherwise it is fine. So the transition rate for helium neon laser is 3.6 into 10 to the power 5 second inverse. Okay, so approximating, we can now like approximate and value of the upper laser level density. Upper laser um, level density, which is equal to, they are written like this, and helium. Okay, so the n metastable helium is helium density. The typical helium single and metastable density, because the heliums are upper laser level density, like the laser level density for neon and helium both should be considered. So the upper laser level intensity, because of the neon laser, has been taken care of into this. And for helium, we got the value. This is the decay rate. AU is the decay rate of upper laser level. And what is this? It is the transition rate, or excitation rate. Excitation rate is not transition rate, it is excitation rate. So decay rate is 7.3 into 10 to the power 6 second inverse. And when we put this thing, this is 5 into 10 to the power 15 meter minus cube. The total upper level density to mid density is this. The stimulated emission cross section I have already mentioned is the value of 10 to the power minus 7 stimulated emission cross section. I have mentioned or something. Okay, the stimulated emission cross section for 632.8 nanometer transition is obtained about 3 into 10 to the minus 17 meters square. So the small signal gain can be written by this. So this is because of this is a cross section, and this is the difference between NU and NL, the density difference between upper level and lower level. So this is a stimulated cross section, and this is 17, and this is simulated emission cross section, and this is excitation cross section. So let me write, otherwise this can lead to confusion that those two cross sections are different cross section. Okay, this is excitation cross section. So this is important to this is excitation rate. Okay, excitation cross section is related to the excitation rate. Simulated cross section is related to gain coefficient. See, this small signal gain coefficient. So 10 to the power minus 17 into 5 into 10 to the power 15 upper laser level density. So here we have maintained assumption that upper layer level density is much greater than lower level density, which will need lasering action. So delta NUL is almost equal to NU. So this is the small signal gain coefficient, which already I have mentioned. So that's how we can obtain these values. So there are another kind of things, the transition probability value and all those. So I don't want to go into this things because that will complicate it more. So application for helium neon lasers. Like interferometry, laser printing, barcode reading, reference beams as a reference. Nowadays helium neon lasers are basically used as pointing and directional reference beams in other optical arrangement. Okay. So nowadays supermarkets also use helium neon lasers as checkout or inventory scanners. And the 15 to 23 nanometer laser is used for the measurement of optical fiber transmission line. 1523 nanometer helium neon lasers are being used for measurements of optical fiber transmission. Sorry. Line. Okay. Then can go to we can like briefly describe argon. Oh, sorry, argon ion laser. Okay, so ion lasers can provide approximately 25 visible wavelengths ranging from 408.9 to 686.1 nanometer, and 10 ultraviolet wavelengths ranging from 275 to 363.8 nanometer. Now, other wavelengths are also produced, but uh, by frequency doubling or parametric conversion of visible argon ion laser. But basically, there's 25 visible wavelengths and 10 ultraviolet wavelengths are we obtain using lasing action between two levels. Okay. It is 408.9 to 686.1 nanometer and 10 UV wavelengths range 275 to 363.8 nanometer. Okay, that at visible region using CW mode lasing action is possible via argon laser, and the power will be 100 watt. Okay, when the output is centered in the visible region. The here also broadening is basically Doppler broadening. Okay, with FW HM about 2.5 gigahertz. The lifetime of this is very less. That's why nowadays argon laser is not that usable. So here the heating is significant. So we need here cooling, significant cooling. The disadvantage is that we need significant cooling for this laser to operate. Okay. So now I will like energy level. So this is ground level. This is E1. Okay. Via pumping, we go to this level of E3, which is very discrete vibrational levels, and there is E2. So lasing action level of this is argon atom. This is ground level of argon. Argon atom is being made argon ion, then that is being pumped. So between these transition levels, like transition can happen this state, and up, and depending on this, we get laser action here. Laser action what? We get different wavelengths because I have already mentioned there we can get after 25 visible transition and 10 infrared UV wavelength. So this is a 4-level lasing action also, and we'll get lasing action between these 2 levels. And this is decay mechanism. So we have seen that argon its lifetime is very less compared to the helium neon laser. So what are the advantages? Why should people use argon ion laser? Ultimately, nowadays ion lasers are being used very less, but at one point of time, why they are being used? Because it emits multiple wavelengths. The output is high, 100 watt is output. Gain is also high. I will give you the number. And it's small in size. On the other hand, disadvantage not only its lifetime is less, but it is costly also. It's costlier than helium neon, at least. The efficiency is less. It's very small. Input power supply. Supply need to be very high. So the applications of argon ion laser, okay, they are treat glaucoma and diabetic eye diseases. Okay. They are used in Raman spectroscopy, holography. They are used as a source of optical power. As I have mentioned that helium neon can be used as a beam reference and all. Here, argon and laser can be used as a source as a optical pumping. So this is the most important point, and others are also important applications. And so now goes to some parameters. I have already discussed the what laser wavelength is there. So inversion density, other parameters, density, delta, NUL by minus NU minus NL or delta NUL is of 2 into 10 to the power 15 per meter cube. Length of the gain medium, 0.12, here also 1 meter. Single pass gain of this laser, 1.05 to 1.65. Gas pressure, 0.1 torr. Output I have already mentioned that it can go up to 100 watt, but it's basically up to 50 watt. Okay. FW HM, emission line with or gain bandwidth, 2.7 into 10 to the power 9 hertz. Okay. So last gaseous transition, I want to, I am not visible. Yes, okay. Gas lasers I want to describe is carbon dioxide lasers. Okay. Okay, molecular densities. So it is not atomic gas laser, it is molecular gas laser. These are all I have discussed. They are atomic gas lasers. And there are also another examples like other examples of atomic gas lasers. are helium cadmium laser, copper vapor laser, vapor laser. Okay, this gives at wavelength, okay, of about 722.9 nanometer. Oh, that's good. Copper vapor laser gives laser wavelength about 510.5 nanometer. Basically, what? There is also gold vapor laser. This gives 627.8 nanometer orange length. Cadmium lasers, they give wavelength 441.6 nanometer, 353.6 nanometer, 325 nanometer. So these lasers are basically CW mode laser, that they are continuous wave laser. But copper vapor laser is pulsed laser. Basically, now I want to discuss the molecular gas lasers. Okay, so molecular gas lasers are like carbon dioxide lasers. There are several molecular gas lasers. Carbon dioxide laser, which I will describe. Excimer lasers. Frozen laser. Far infrared gas lasers. Chemical lasers. Okay. So now I will describe the carbon dioxide laser. Mm. So carbon dioxide laser is basically there is nitrogen and also carbon dioxide. Okay, there is vibrational level. This is 10.6 micrometer. This is level 8. Okay, so carbon dioxide laser. There is like three modes: symmetric stretching mode, so this is carbon. This is oxygen. Okay, so this is like symmetric stretching. So the molecule vibrate in different modes in in the circumference. One is symmetric stretching, one is bending. So this dot line are when they are like how they displace. So they are oxygen, carbon, oxygen, this is oxygen, this is carbon. This is bending. Okay. And another is antisymmetric stretching. Okay. So for antisymmetric stretching, the carbon molecule also, for symmetric stretching, carbon molecule doesn't displace, but here carbon molecule also get displaced. In bending also that get displaced, but bending doesn't happen in linear mode, right? So anti-symmetric stretching. So the when symmetric stretching bending correspond to 1, 2, this is pi mu 3. So the symmetric stretching mode, it gave us the value 1337 centimeter inverse frequency. Bending mode frequency is like 667 centimeter inverse. Antisymmetric stretching is like 2349 centimeter inverse. Okay, So because of this, we get three kind of energy levels. Each electronic level has a number of vibrational levels that I have shown. Each electronic level has number of vibrational levels, and each vibrational level has a number of rotational level associated with it. So, in carbon dioxide laser, the laser uses carbon dioxide gas mixed with nitrogen gas. The active centers are carbon dioxide molecules, and by active centers, I mean the lasing action, lasing transition occurred between a rotational level with associated with a vibrational level, and the rotational level associated with a lower vibrational level of an electronic ground state of carbon dioxide molecule, not in the nitrogen molecule. Okay. So when a discharge is passed through the tube, I already have mentioned in atomic gas lasers. Similarly, in molecular gas lasers, the molecules are kept in a tube. The molecule, when the discharge is passed in a tube containing carbon dioxide, the electron are collisions excite the nitrogen and carbon dioxide molecules to higher vibrational rotational level. So keep it in mind that they are not changing electronic levels; they are changing the vibrational level in the same electronic level. Okay. So then the collision cross section for the excitation of carbon dioxide to the level A, this is the level A, is very high. So this level also, this is the nu3, the level is corresponding to nu3 or antisymmetric stretching. So where the population of the collision cross section is very high, and this is also like also overlap with the nitrogen higher vibrational level corresponding to nu dash dash 1. So there is energy transfer. Like in helium nitrogen neon laser, the lasing action happened in the because of the neon atoms, but helium atoms transfer the energy. Similarly, here nitrogen atoms transfer the energy to the carbon dioxide molecules. Okay, so the energy gets like um, they transfer, and the population because of this, and the B energy level, this is correspondence to nu2, or I can say that because of the bending, this energy level happens, and because of the symmetrical staging, this energy level uh, now this is for carbon dioxide, and because of pumping neon nitrogen atoms also go up to the higher vibrational levels. Carbon dioxide laser also goes to the higher vibrational level, but this A level coincide with this nitrogen level, and they energy transfer means molecule transfer, photon transfer. So the population inversion happen between this A level and B and C level. So when the molecule, carbon dioxide molecule goes from this A level to C level, we get a laser wavelength of 10.6 micrometer, or we can say nanometer, and this is 9 nanometer angstrom. Okay, it's better to keep in micrometer. You can like change the conversion with other. So lasing action happens between this A level and C level, and A level and B level. Okay. Now let us give you some let me give you some numbers because of this action. Okay, now in a brief, I forget to mention something like molecular gas lasers, molecular lens gases. They are like they can produce two kind of wavelengths: middle infrared laser, middle infrared region, and far infrared region. Okay. They are can operate at very high pressure because the energies of the upper laser levels are much closer to the ground state of the carbon dioxide molecule, and then are energies of the upper laser level of atomic lasers. Their radiative lifetime is very short, so of the order of 10 to the power 9 minus 9 second. So specification of carbon dioxide lasers. Okay, so laser wavelength is two discrete wavelength. One is 10.6 micrometer, another is 9.4 micrometer. Okay, carbon dioxide and nitrogen gas ratio is about 0.8 to 1%. Okay, these are these sources. And a quick note, there is another class of laser that is carbon monoxide laser, which gives the laser wavelength 5 to 6 micrometer. How about the is given? The carbon monoxide dioxide can be laser excited lasers, can also be guided laser, transversely excited laser, longitudinal excited gas dynamic laser, and they are kind of many things. Uh, but every time the mechanism is same. There is a nitrogen and the carbon dioxide. The nitrogen upper level nitrogen new dash dash one vibration level is sufficiently excited and but it is susceptible to radiative decay. So by collision they transfer energy to the carbon monoxide level, and population inversion happens. So here laser. Okay. So operation, they can operate as CW and as well as pulse. Output power varies between 1 to 10,000 watt. Single pass gain 1.326. Inversion density is of the order 3 into 10 to the power 21 per meter cube. pumping method. Excitation, collisional transfer, gas pressure. As I have mentioned, they are not low gas pressure, 50 to 760 torr. Atomic gas molecules, gas lasers were low gas pressures laser, but molecular gas lasers are not. Gain medium length, point 3 to 2.0 meter. Okay. Gain bandwidth, six into 10 to the power 7 hertz. Stimulated emission, cross section, 3 into 10 to the power minus 22 meter square. So the applications of this laser, material processing, cutting, drilling, etching, welding. So remember, the I have discussed in the, detail three lasers: helium neon, argon laser, and now carbon dioxide laser. Helium neon lasers are used for different kind of purpose. Argon lasers, argon ion lasers are used different kind of purpose. If at least try to remember the area, like Raman spectroscopy. If you write the carbon dioxide laser is used in Raman spectroscopy or in treat to glaucoma, it's very wrong because the wavelengths are different. And there is another kind of thing that these are infrared or middle infrared. So like these are far infrared and middle infrared range lasers. So it cannot be used to treat glaucoma and all other thing. There is a prescribed graph or at which wavelength water absorbs most and water doesn't absorb laser wavelength, and depending on that lasers are used on human body at those particular wavelengths. So never ever jump uh, get confused between this. Like carbon dioxide laser is are used for etching, welding, melting, and all those things. It cannot be used on human body. Now, let me describe some other molecular uh, gas laser in briefly. So, atomic gas laser, molecular gas laser, they are all low density gain medium. Solid state lasers are high density gain medium. Excimer lasers, they are a group of pulse lasers that incorporate electronic transition within short-lived molecules like halogen atom and a rare gas atom, or like combination of those. The word excimer is a contraction of the phrase excited dimer. The excimer came from excited dimer. And this molecule, which is a combination of rare gas atom like argon, krypton, or xenon, with the halogen atom, which is fluorine, chlorine, bromide, or iodide. They are in molecules are in excited state because they cannot be like in ground state. They are short lived. The ground state is externally extremely, actually it's not externally, very short lived. Basically mm, they emit ultraviolet wavelengths, excimus, spectral region. Some very few operate in the visible region. So, like XEF, excimer laser, give us 353 nanometer generally. Some operate in visible spectrum. For xenon, fluoride 308 nanometer, chromium fluoride at 248 nanometer. This is ultraviolet range. Both are like basically they are in ultraviolet range. Argon fluoride at 193 nanometer. Fluoride only 153 nanometer. So basically, they are not low pressure lasers; they are high pressure lasers. But like chromium fluoride works at 2 atmospheric pressure, 2 atm pressure. Fluoride at 10 torr, argon at 30 torr. These are partial pressures. And helium approximately at 1400 torr. So what happened that the excimer laser is produced by forming this excited state species of the excimer molecule in the upper laser level. As I have mentioned, the ground state of this molecule is not stable, and it is not possible to produce the upper laser level by direct pumping from such a ground state. When ground state is not stable, so we cannot pump from ground state to higher level state. Okay, upper level state. So these molecules are formed already in the upper level. So pumping is not necessary, but indirect pumping is necessary. So laser medium here includes noble gas atoms such as argon as well as fluoride molecules in the form of fluorine. When electrical discharge or an electric beam is initiated within the gain medium, the noble gas atoms are excited and ionized, leaving, for example, argon plus or argon minus, and the fluorine molecules are dissociated to produce fluoride atoms. These fluoride atoms rapidly collect a free electron and form fluorine minus, and the argon plus and fluoride minus, they produce argon fluoride, and they are already in upper laser level. Okay, then argon fluoride molecules subsequently radiate and leaving them in the ground state, and they dissociate already. So this is how the population inversion maintained in the excimer laser. First argon become argon plus, then fluoride. This electron comes here, fluorine minus, then argon plus and fluorine give rise argon fluoride, upper level. They come to the ground state and dissociated. This is how the mechanism of argon excimer class, not basically argon fluoride lasers. So basically we get here the infrared middle or ultraviolet, the middle and infrared wavelengths we got from the carbon dioxide laser. Here we get ultraviolet wavelengths. So here like basic for typically single pass gain for this lasers is about 3.3 to 90. Okay, gain medium length like 0.5 to 1 meter. Okay, small signal gain coefficient 2.4 to 4.5 nanometer. Gain bandwidth 10^13 hertz. Output power, basically they are pulsed laser, 1 joule per pulse at 100 hertz. Mode of variation is pulsed. So now I'll discuss the applications of this laser. For medical application, photolithography, pumping of dye laser, and etc. Okay, other kind of molecular gas lasers I have already described is one of this is nitrogen gas laser. Okay, there is argon. Okay, rest and say in which region it is. It is also give in the ultraviolet region, that is 30. It's give a wavelength 337.1 nanometer. Okay, it is also a pulsed laser. So they are usually used for pumping compact tunable dye lasers. They can be manufactured in relatively small size and sealed off laser tube that operates in a long lifetime. That's why basically used in uh, pumping dye laser. Okay. Another kind of laser is far infrared gas lasers. So they have almost 20 kind of transition, and already in the name they give laser transition in the far infrared range, that is 99 to 373 micrometer. Okay. Again, I'm not visible. Okay. So the see the wavelength range is far more in the infrared than the carbon dioxide laser. So they are pulsed and also CW. These lasers, most of them are not operate in TEM00 mode, but far infrared gas laser operate in TEM00 mode. Okay. So the far infrared gas lasers used in plasma diagnostics, spectroscopy of semiconductor, atmospheric spectroscopy, heterodyne sources, far infrared astronomy, and all. And then next is chemical laser. So they gave like deuterium laser used can shoot 3 point give 4.2 micrometer. Hydrogen bromide laser operate at 4 to 4.7 micrometer. Etc. They are like in a chemical reaction. The chemical lasers are you can say that hydrogen bromide can be a excimer laser and all, but these chemical lasers typically operate on the basis of chemical reaction. So they by the chemical reaction, these hydrogen fluoride or deuterium fluoride lasers are produced with hydrogen gas with fluorine gas, and then they give lasing actions. So other low density gain, other gain medium laser. Atomic gas lasers and molecular gas laser is already low density gain medium laser. Other gas lasers are like X-ray, plasma laser. Okay, and there is another thing. Okay, free electron gas laser. These are the laser. Free electron gas laser can is a tunable laser, but their size is very large. Tunable laser. So they are kind of low density gain medium lasers. High density solid state lasers fall in the high density gain medium laser. So let us stop today, and we can discuss the high density gain medium laser at the next class, and also the like assignment problems. Thank you. Thank you.